Hello, I'm Ed Wicklein with Corello Engineers, and I'm here today to talk more about the Technical Guidance Manual on Computational Fluid Dynamics Modeling for Chlorine Contact Basins that we've been developing with the Colorado Department of Public Health and Environment. Today, we're going to be talking about the geometry and meshing of the model. So the sample problem that's included in Appendix B of the guidance document is this tank that's 50 feet by 50 feet by 10 feet deep. Today we're going to work through the geometry, building the mesh, and looking at mesh quality, then exporting it so it can go to the solver. We use Trelis as our meshing software, but there are many others available. Often we develop the geometry in this software as well. There's many tools here. So we can create our volume. It would be a tank 50 feet by 50 feet by 10 feet. Please note the units that you're using, and it creates a volume here for us. The model defaults to the centroid, so typically I would move it to a nice coordinate point, so 25, 25, 5. We put it at a location where this corner is at 0, 0, 0. Our tank geometry, if we take another look at it, has a 18-inch diameter inlet pipe and 18-inch diameter outlet pipe, both centered on these passes that are 5.56 feet wide. And so we would continue developing the geometry. We also like to decompose the geometry to help facilitate meshing. So if our tank is, if our passes are 5.56 feet, there's a couple different ways to cut this out to define the walls. We can cut the tank assuming a 2D wall. And the XZ plane. And so if we pick 5.6, it would cut the model here. Would be one way to do it. If we wanted to make a wall with a thickness, we could create a wall and subtract it from the domain. There's a couple ways to do it. So typically for this problem, I would cut it up at a series of points, 5.56 feet along. So we can come along here and do the calculation. The next one would be 11.12. That one's right. And we'll continue working through the tank that way. We also need to create our inlet. And again, there's a couple ways to do this. We could create a cylinder that is 18 inches in diameter, so the radius would be 0.75 feet. And in this software, you don't get a lot of options on where to start. If we want it 10 diameters long, that would be 15 feet. And so we create it, and it creates it at the centroid again. So we could move it. At the y-axis and shift it into place. $15 feet, so it's 2 feet off the floor, so the Z direction would be it up, and it would then move over to the center, which would be over 8. And finally, it needs to go back so the faces meet up. And that would be our inlet location. And so we would be able to come in here and we need to assign boundary conditions. Different meshing softwares have different ways to do this, but we would select our velocity inlet, and there it is. Apply. Over on the left, we've got our tree. We could come here to check that we set it up correctly, expand our boundary conditions, velocity inlet right there. So the flow comes in. Then these two volumes would need to be joined, and we would continue decomposing the geometry. And so there's bends at 5.56 feet again. These volumes at the ZY plane. We cut there. We could also cut these at the other end. And so now we've got our first pass and our second pass defined. We would need to have a boundary condition here to prevent flow from traveling this way so it follows the serpentine path. And so we could add a wall. And assign a wall to those two. And now in our boundary conditions, we have our baffle wall defined within here. And so we would continue working through setting up this geometry to come up with a complete problem. Make sure to save, of course, as you work. We will open the decomposed geometry once it's all been created to speed up our time here. And so this would be the completed geometry with all of the surfaces decomposed. We've applied all of the boundary conditions. We've got baffles through this system, so flow will be forced to take the serpentine path. We're going to be using a rigid lid approximation as mentioned in the last module. So we've assigned the surface as a wall boundary called surface. Got an outlet boundary we've assigned at the outlet pipe here. So the flow will enter from the inlet, travel through the domain and exit there. Now that we have this geometry decomposed, we need to begin the process of developing mesh. Again, there's a couple of ways to do this. Different software packages have different approaches. Some just use or want to default to a uniform cell size, but we need to make sure that we have a good high quality mesh. So we're going to enter some additional information. I have initially defined some of these boundaries. So often we'll define it by the edge. And so, or edge size, either number of intervals or element size. So on this edge, we've defined 16 intervals or elements with a size of 3 inches on the wall of the pipe. We've defined 36 intervals around it for a little over 2 inches for our size. It can be helpful to use boundary layers on curved surfaces to help maintain a high quality mesh and capture the edge effects. And so we have a couple boundary layers we've predefined. So we would pick our volume, assign it. And we can see that these elements are set there. It looks a little bit coarse, but if we're using 36 elements, it ends up a little bit smoother. Then it's time to generate the mesh. There's a number of methods of meshing, of course. For this problem, we're going to be hexahedral mesh. And so we would use a pave option and mesh our surface. It defines the mesh on the surface. We do want to pay attention to quality. There are elements here that are somewhat askew. But if we check our surface mesh quality, we end up with 0.9 on the shape. We'll monitor that as we develop the mesh. So we'll want to use a sizing function or set the approximate number of elements on this face. And if it's 15 feet long, we're using a 3-inch or finer. We end up with 70 elements approximately. Define the mesh on the face with a map. And we get an error. Probably previously defined since we're working off a partially built model. And so it defines a map mesh. Then within this volume, we'll sweep it to create the volume. There's controls for defining which face it's sweeping from and to, or it may default, and so it generates this volume mesh. It's now swept from here to here. Check the quality. The main quality metric for hexahedral elements that we're going to be concerned about in this case is the equal angle skew, which is roughly equivalent to the orthogonality. And so we see here that the maximum value is 0.43, which is under 0.5 or 0.6, which is the target range we're looking for. So we would consider this probably a good quality mesh. The other volumes, we've defined the edges. Again, we've got 24 intervals or 3-inch size. This mesh is approximately 3-inch. And so we would come here and use a map feature to develop a uniform mesh, uniform hexahedral mesh of 6-faced elements. We'll check our quality here. We know it's going to be pretty good. And so we're at 2.75 to the minus 13. So effectively, all of these elements are perfectly square. So that would be considered a very high quality mesh. We'll go through the model and mesh out all the components, working through. So we end up with a continuous mesh. Save as you go. And we would work through all of this. And I'm going to jump to the end. And we have our complete mesh of our chlorine contact basin. We'd go through our quality checks. If there were any tetrahedral elements, we'd look at equal volume skew. For the hexes, we're looking at the equal angle skew. Each software does have its own particulars, what is considered sufficient resolution or sufficient quality. And so we would export this mesh to the format that's needed for the solver to look at it or to open it. And so here we've gone through the geometry creation, building the mesh. We've done the quality checks. The mesh is good, so we're ready to go to set up the model in the solver. We'll take our initial run through. Everything's converged. We would continue the mesh independence. And then we'll update this mesh to make sure we have sufficient resolution to solve the problem before we proceed into the actual flow conditions of interest. So our next module will be setting up the CFD model itself. Thank you for your time.